So we'll restart. Let me, before we start, in case some of you actually took a break, there was there was a question with regards to what happens when when the poll is not just a simple poll. So this example that I gave is not a very good example because I made a typo in how I wrote here. The example I meant to give was the example of f of z being the one I have here. So let me loop around it so that you can see. This example of f of z being equal to e to the z over z minus a times z minus b, because it's a more interesting example. Here, this e to the ab is just a constant. And it took this example from the book so that you could go and see the calculation for when a is equal to b, and I wouldn't have to do it so that I can go to the other things. But then I wrote here this other example, and we computed we computed the residues when a is different than b for that one, But if we were to compute for the actual one that's on the book, and I meant to write, it would be a similar calculation, So it's perfectly fine that we computed for this other function, I mean, I guess it helps convey how it's so easy to compute these residues because even if you write the function incorrectly, it's still easy to compute. It's not like the example was very brittle or anything like this. Now, when a is equal to b, in this example, of course, the residue is just 0, Because you just have a constant over z minus a squared, So if a is equal to b, then the function f of z is just equal to e to a over z minus a squared, and so the residue is just 0. And so it's very easy to compute. For this one, it's a little more interesting calculation, and it'll be shown in the exercise classes. I mean, one trick is you can just one thing you can do in general is just take Taylor decompositions, truncated Taylor decompositions of the function, And if you do that, then it becomes very obvious which part is the part that corresponds to a 1 over z minus a term, Because taking Taylor decompositions of this is sort of is a big hassle because it has these quotients and so on. The idea is you take just a Taylor decomposition of something simple in the function, That's not a polynomial like e of z. You take it, say, around a, and then you just divide the Taylor decomposition by that, And then you get exactly what you want, So, I mean, I don't know if it's worth me doing the calculation, but yeah, maybe. So, So if I have f of z equals, say, now e of z, in this case, over z minus a squared, You just take the Taylor expansion of e of z around a, so this should be, e, Think of this as ea, e z minus a, e of a plus e of a z minus a plus, the square terms then stop mattering, so you just have, some function, We're doing the truncated example squared, And so if I do that, then if I take this and I divide by z minus a squared, what do I get? I get e of z over z minus a squared, equals e of a over z minus a squared plus e of a over z minus a plus some f2 h z, sorry. And then you can just compute, you directly compute the residue from here. The residue becomes e of a. Okay. All right. Sorry for the earlier confusion of the I had put one function down and now I had my notes on the other one. Okay. All right. Any questions? Is this clear? Okay. All right. So let me go to a new page. Okay. So let's see, because I ended up not looking at what I was going to do after the break. Give me just 1 minute. Before. Okay, before we go to series, there's still something I want to convey before we get to series. And I mean, this oftentimes goes under the name of argument principle. Okay? And the thing I want to convey is the following. Right? Okay, let me get 10 seconds to think about how I explain this in a way that I don't just write down a calculation. So, okay, I've convinced you already that, when we did this residue calculus stuff, that at least Cauchy integral formula comes for free from it. Now let's continue collecting, things that come for free from it. And another thing that comes for free is the stuff we did about counting zeros, right? So when we counted, when we counted zeros of a function, when we counted zeros of a function, f inside a curve, that is also this is exactly what we did as well, right? We sort of already used the residue calculus, right? We did, I mean, in a way, residue calculus. Okay, let me try to convince you of this. Okay, so let's take an analytic function. Let me change to another pen. So let's take f going from omega to c analytic, right? Usual suspect always, right? And now the function, right? The function f prime of z, f of z, has a pole of order 1. Exactly when f has a 0. Okay, why? And moreover, the residue will be the order of this 0. Okay? Why? Let's say that f of z has a 0 of order h at z equals a. Okay. Then this means that, right, f of z is equal to z minus a to the h times f of hz, where f of h of z is, non-zero and analytic. Okay. So I should say, of course, okay, this is analytic and not identically 0, right? This is also, otherwise we're in trouble. Okay, not identically 0. So let's say we have this, right? Then let's look at what f prime not h, sorry, what f prime of z over f of z is, right? At a. Well, okay, let's just expand, right? This is z minus a h f h of z, right? Let's derivative like this, okay? Z h f h of z. Okay, this is equal to h. Okay, let's differentiate term by term. Like there's right. This is the differentiation of that term. So h z minus a to the h minus 1 f of h of z, right? Plus z minus a h. Now the derivative of this. Okay. H. Oh, I don't know what's happening. Oh, wait, let me make sure this goes well. Sorry. H of z. Okay, so now, right, we can cancel a few terms. So we get h, right, the FHZ cancels out. We have h, right, z minus a, right, because right, there's an h minus 1 on the top and h on the bottom. And then the other term, the z to the minus ah cancels out, and we have fh prime z over fhz, right? Where now this, right, there's no poles, right? This is analytic now, right? Because then, this thing is not 0, right? fh of z is not 0 at a. Okay, and so the residue, not only this has a pole, but the residue of fh of z over f of z, right? When z is equal to a, is actually equal to h, right? The order of the 0. Okay, and so this means that when we integrate, right, now you're seeing, right, when we integrate this function f prime of z, the logarithmic derivative f prime of z over f of z, right, in a curve, we get exactly, we'll say 1 over 2 pi times that, we get exactly the sums of the residues. So we get exactly the values, the sums of the orders of the zeros, right? So it's counting the zeros with multiplicity, and this is exactly what we saw, right? We saw this theorem, we did it sort of by hand, but now it follows directly from the residue, right, from the calculus of residues. But now we actually prepared to go a little bit further, right? Which is that this all holds, right? This all holds if f of z has a pole of order minus h, right? Because the whole thing still goes through, right? If f of z instead of a 0 has a pole now not of order h, but of order minus h, right? Then, you know, this is exactly true, the formula, right? We can write f, because f has a pole of order minus h, we can write f this way. The whole thing goes through, right? Nothing changes. And so if f, right? So if f has a pole of order, let me call it, I don't know, k, just to not use minus h, right? Around at z equals a, then, right, exactly what we did above says that the residue z equals a, right, of the logarithmic derivative, right, is equal to minus k, sorry, right, because the pole order was minus h, it gives the residue h, right, nothing changes in the calculation, so the residue is minus k. So the logarithmic derivative has this power that when we look at its residues, it tells us, you know, gives us the order of the 0 or of the pole. It gives us a negative, if it gives us a negative integer, if it's the order of a pole, right? If it's a pole and that what integer it is tells us the order, and it gives us the order of the 0 if there's a 0. Right, I mean, again, let's go back to a bit of intuition. Why? Because if you think of, you know, f as being, for example, a polynomial, right? If it contains a factor of z minus a to some big power, when you take the derivative, you just shove off one of those factors, right? So when you take the derivative over a function, everything is always going to be of the type something over just one factor of z minus a, right? Because the derivative will always have one less factor or be 1 over the, right? If you think of, you know, I mean, it's the same thing for like polynomials or 1 over polynomials or polynomials in 1 over z minus a. But if you think of a polynomial of degree n, right, the derivative will be of degree n minus 1. And so when you take the derivative over f, nothing ever shows up that it's of order, you know, something like 1 over z minus a squared or something like this. Right, and in particular, the term that shows, even a term, or I should say, even a term that was of with a high degree is transformed into a term of just degree 1 or degree minus 1. And the coefficient, because of the way the derivative works, is exactly the order of the term originally. Okay? And so what you get immediately out of this, right? So like there's a, you know, we get a generalization of the thing we showed for counting zeros. And we get that this is a very nice theorem, right? That's also theorem. So if f has, you know, it's defined in some omega, and he has zeros and poles, right? So it's meromorphic. Morphic in omega, right? With zeros, say aj, and poles vk, okay? Then counted with multiplicity. Right? Then, you know, if I integrate around the curve Of course, needless to say, right? The curve can't intersect the poles, right? The curve is inside omega and doesn't intersect the poles. Okay, and I integrate f prime of z, f of z, dz. Then the value of this is the sum of the residues, right? The value of this is the sum, you know, let me do it this way, right? The sum of, yeah, let's say points, I don't want to call them A's or B's, let's call them C, let's say omegas, okay? The sum over omegas, zeros, or poles, right? Because these are the isolated singularities of f prime z, f prime of z over f of z, right? The residue of right, of this function at z being one of these w's, okay? Okay, I mean, I'm not being very, the notation isn't so good here, but it'll become better in a second, right, in the next equality, right? But what is this? Well, if something is a zero, then the residue will show up as being the order of that zero, right? But because the zeros are counted with multiplicity, all I'm doing, oh, I need the winding numbers, of course, sorry, right? I need, of course, the winding numbers, okay? And so, right, and so we have the sum over j's of, right? Because if it counts, this is one, like this term here is one, if the, right, for the j that is, for the zero that's simple, if the zero is of order 10, this term here is equal to 10, and this, in this sum, this shows up 10 times, right? So this is the same, okay? Minus sum over k, right? And then the poles show up negatively. Okay. Okay. And now, you know, this term might or might not help. I'm not sure. So feel free to ignore it. Maybe I'll just jump. So you know, feel free to ignore this. I'll just jump straight to the other one now in explaining. I won't go through it, right? So we're integrating this function by the calculus of residues. We know that, right? So we're integrating this. We know that it's the sum of the residues around the points, the isolated singularities. The isolated singularities of f prime z over fz are exactly the zeros or the poles of f of z, right? Because it has no essential singularities. And each zero shows up in the calculation, the residue around each zero is equal to the order of the zero. And in this sum, it gets summed exactly the number of times because it counted with multiplicity, right? And the poles show up negative of that. And so this means that the integral of the logarithmic derivative once I divide by 1 over 2 pi I is just the number of zeros minus the number of poles inside the curve, right? I mean, in particular, you know, if you have any curve, you can just, you have this formula with the winding numbers, but, you know, most useful when the winding numbers, right? When the winding numbers are 0 or 1. I'd say you want to count the number of zeros or poles around the circle. Okay? And so this is a very nice result, and it has a name. It's called the argument principle. Okay, and so and it's this, you know, it's basically what we did for the zeros, but now we can almost for free get it also that if there's poles, you get just a minus sign. Okay, the reason why it's called argument principle is if you see what happens, you know, if you take this, right, when we looked at the counting the number of zeros, we took this to be, we thought of it as an integral in the image, right? F sent the curve gamma to some other curve big gamma in where, right, in like the space W equal F of Z, right? And it was basically counting how many times this loops around zero. right? And it loops around 0. You can view it as sort of looping the other direction around infinity and so on. You can get some of you can interpret this that way, and that's where the name is coming from. Okay, so now now this has a nice. I mean, I don't want to get too much into it. I think you'll see more of this in the exercise class, but this has already a nice few implications. One is the so-called Roche's theorem, which you'll see in exercise classes. But maybe another one that comes almost for free. So let me just briefly explain it. Is that if you have a function g, g of z, or g, let's say, if I have a function g in this domain, going to see analytic, right? For any function z, then the function, if instead of taking the residue of f prime over f, I take the residue, right? If I take the residue of, or maybe let me write this way, the function g of z, right? F prime of z, f of z, right? It's not so hard to see this has residues, basically GA F, GA H hat if A, if A is a 0 of order H of F, and minus GAH if A is a pole of order H. Sorry. Of F of F. Okay. And now the nice thing is if you take, right? So now you can get formulas, right? You can get very nice formulas of you can use this theorem here and basically add a function gz or g of z hitting the logarithmic derivative, and what you get on the other side is the values of f and g, right, of g at the zeros and the poles, and so it can tell you quite a few things, right? You get many formulas from this. So you'll see a few more of these in exercise classes, but a useful formula is you can say something about you can actually say something about the inverse. Okay, so let me see if I can do this very briefly. Let's see how this goes. So if I take, let's say that I take, f of z0 equals w, but you'll see more of this in exercise class. I just want to convey how you can use these formulas for things that might not seem obvious at all. So let's say that I take f of z0 equal w0, right? And let's say that that the derivative I want to invert, so I don't want to deal with branches and things like this. But there is a way of extending this for when there's branches. And let's say that the derivative is non-zero, right? Then we know, right? We showed that then there exists some delta such that for delta minus delta 0, w minus w0 smaller than delta, there is an inverse. Basically, there exists only one solution, to fz equals w in z minus z0 in some epsilon, for some epsilon. Okay. Okay, for some epsilon. Okay, so we saw this. Now let's apply the theorem. Now we apply the theorem from above for, I believe it's f of z equals z minus w. Okay. And g of z equals z. Okay, so the zero, right? So now around that little, in these little neighborhoods, the zero of f of z is exactly at w, right? And so now let's take, let's take now a circle around z0, epsilon, right? 1 over 2 pi I, right? And now maybe I should have a dummy variable will be better. So, okay, maybe it's best if I use a dummy variable here to not get very complicated. No, not, oh, sorry, that's why. Okay, so I'm gonna use, yeah, use above theorem for, okay, I should say this instead. Problem is there's two F's. Use for function f of z minus w, right? So that's a function whose zero is the solution to our equation. Okay, and so now if I do this, the derivative, if I do this, the derivative of fz minus w is just f of z prime, right? The w doesn't matter, over f of z minus w, right? dz. Okay, but now what is the zero? There's a zero because the derivative is the derivative is non-zero. The derivative will be non-zero in the neighborhood, so the zeros are all simple, just of order 1, and so this will be equal to the the winding number, which is 1, because I'm looping around z0. I need g here, right? Maybe, yeah, equals to, I don't know if I should, maybe I should write g, right? Equals of g at g of z, right? Where this z is the solution of fz equals w. Okay, so I mean, there's a few, so let's make this a dummy variable here. So let me rewrite this, 2 pi I cz0 epsilon, right? Let's, instead of z, let's do this dxc, like how we did for the Cauchy integral formula. And so now we have f prime of xc, right? F of xc minus w. And now we have xc here, right? Because g of xc is just xc equals z, right? But z is now a z of w, right? Because z of w is the equation, it's the zero of this here. Is this the equation of z, right? And so this means that in a neighborhood, right? If I want to take, this is just like the inverse, right? W. And so this means that if I want to, at least in a neighborhood, I can define, right? I mean, I'm being a bit hand wavy. You'll see this more, done for more, in more generality and so on in the exercise classes. But, I get immediately a formula. If I didn't do any calculation incorrectly, for the inverse function, right? So an integral formula for inverse function. And when when f of z is not so, okay, let me see if I want to say any other. Okay, in the neighborhood. I mean, this is all in the neighborhood, of course. Okay, now an interesting question in pursuing, trying to understand these inverse functions through this way is what happens if this is dropped, right? And then we know if this is dropped, there's this right? And basically, there's these branches, right? Where instead of just one solution in a neighborhood, there's two solutions, right? And so because there's two solutions, this means that there'll be two zeros to this, right? And if there'll be two zeros to this will be a sum over the two zeros, right? So here they'll show up a sum over the two zeros, right? And so you get a formula that gives you that this integral is equal to basically some sum of a function of the possible values that the inverse could take, if you think of it as a multivalued function. And then if you take g to be different functions, you get different sums of functions of the inverses, and you can get some conclusions that way. Okay, so let me just leave it at that. Okay, I saw a question just now. Why is the integral equal to? Yeah, okay. I realize that the problem is when talking about these inverses and so on, the notation is either I overload notation or there's maybe a bit too much ambiguity. Okay, so the question is why what do I mean by this? Why is this the case? Okay, so yeah, this z, maybe I should do a little prime on top. This z is the dummy variable inside the integral, right? And so I know, right, so let's look at this. So I know that f of z0 equals w0, and say the derivative is non-zero, then in the neighborhood, there is only one solution to the equation given w. What is the z such that f of z is equal to w, right? Let's call this z of w, right? Then I take the function g of z equals z, maybe we should think of the dummy variables, and f of z minus w as the function I'm going to use this argument principle on. Okay? And I'm going to use this sort of argument principle on steroids in which I multiply also by a function here. Okay? And now what do I get? If I do that with the function fz prime minus w, I get 1 over 2 pi I integral of, g times the logarithmic derivative of this function, this logarithmic derivative, okay? It's equal to, right, there's only one zero, right? In this neighborhood, there's only one solution to this, right? There's only one solution to this equation, which is only 1 0 to this. There's no poles because this function was analytic. And so in the argument principle stuff, there's only one term, right? Which is the winding number of the curve, right? But the curve is the curve that goes around the neighborhood. And I know there's exactly one solution there. So the winding number is 1 times, and the order of the 0 is also 1 because of this, right? So I get that the value of the integral, the residue, is equal to GA times this H will be 1, right? And so this is just equal to G of the solution. So I should say G of Z of W, right? But this is equal to, because I picked G to be just identity function, this is equal to Z of W. So this allows me to write the Z that is the solution to the equation f of Z equals W, right? Given a W, it allows me to write it as an integral function depending on W and F, right? And then this is just equal to Z prime, right? And then I just, instead of having all those primes, I just define the new variable C, becomes a bit easier to keep track of, right? And then I get this equation. Okay, I think it's clear now from the reply I got. If anything is not clear, please interrupt. Okay, I mean, when working with the inverses, it's almost better to just, you should sit down and try to work it out because the notation gets so heavy that, it's much harder to just follow someone else doing it. And conceptually, there's really not much going on. Okay. Okay, so if if f of, maybe I should say, if f of z0 is 0, we'll see in exercise class a bit about this. But basically, there'll be many solutions, so you'll get some kind of sum here. That's the punchline. You can just try to work it out. Okay. Okay, let me make sure I don't forget anything. So now one of the applications of this, is actually working out definite integrals. over reals. Right? And there's things like maybe I have some integral of a complicated function. Let's say I take here the reals. Okay, and you take maybe, the integral from, I don't know, minus r to r of some complicated function. Okay, and you're doing some integral from minus r to r of some function, whatever it is, even over the reals. Then there'll be times in which you can define maybe some other curve, right, in which it's actually much easier to compute, say, the integral over this, right? But maybe the function ends up having, isolated singularities here and there or anything like this. You use calculus of residues to compute the integral around the full curve, maybe going this way and then this way, right? It gives you the value of that integral. And then because it's for whatever reason easy to compute in, say, this other curve, you get the value of the integral over the reals, right? And so this is the kind of thing that, there's no better example. There's just many, many examples, and you work out many examples, both in exercise classes and in the homework, right? But in fact, I believe this was Cauchy's motivation, right? Was to compute integrals that he had no other way of computing. And so one of the main applications of calculus of residues and argument principle and so on is the computing of definite integrals. Okay? Now, I don't think it's the most useful for me to just work out a few examples and write them out because, just calculations. It's just examples that one needs to work out. But you'll see in exercise classes where a bit more participative with smaller groups is better for that kind of thing. Okay. But you'll definitely see examples of it. And now you have all the tools to compute these seemingly, looking almost impossible type of integrals. Okay, so now, there's very famous examples involving exponentials and trigonometric functions and all this. Okay, so now in the last 7 minutes, because I want to do this before the end of the week, we'll talk about the goal of what we're going to talk about now is series. Right? In particular, I want to talk about Taylor series. Right? So not just truncated Taylor series, but actually infinite series. Right? That were all very used from real analysis. But I want to, in particular, I want to show the big, the big theorem in what I'm about to explain is that essentially every analytic function has a Taylor series, right? So the goal will be to show that every and this is a very powerful and the Taylor series will be defined in a certain domain of convergence that we'll understand. Okay? But before we talk about series, right, we need to start by talking about sequences. Okay, and so there'll be a little bit of housekeeping to do. Sequences of analytic functions. Okay. And so the idea being that if we have fn of z, right, converging as n goes to infinity to some function f of z, right, we want to understand when is it, right? We could have, say, pointwise convergence, right? For every z, this sequence of numbers converges, right? I'm sure you've seen different types of convergences in, analysis and analysis class. We want to understand, when is it the case that the limit function f is analytic? Right, so clearly this is not, it's not always the case. If pointwise, of course, like I'm sure you've seen all these examples in analysis, right? Pointwise, pointwise convergence isn't enough. Right, there's also, even in real analysis, there's lots of examples where functions will converge pointwise, but they'll be very nice, continuous, differentiable, whatever, but the resulting function isn't. Right, just take things like, things like x to the n between 0 and 1, or x to the 1 over n, or minus n. All these examples have issues. Okay, and now, okay, Now, usually, right? Usually, one asks. I'm just making a few points. Usually, one asks for uniform convergence, right? Uniform convergence. Again, I'm sure you've seen this, but it's just that, right? So pointwise convergence says that for every point, we talked about this even a bit in the beginning, right? For every point z, it converges, right? So for every epsilon, there exists a delta type argument. Uniform convergence means that you can pick the same delta for all epsilons. You can pick a delta and then it works for all the points z, right? So when you're trying to work out, integrals, derivatives, limits, anything, you can always bound uniformly the error terms. So uniform convergence is usually asked for, and when when you have uniformly convergence, then everything is fine, right? And that's easy to show. Okay, but we're going to want to ask a little less. Right? It's perfectly fine if we don't actually have uniform convergence. In particular, for some examples, right? So what are we after now here? We're after a theorem, right? So of course, if these functions are defined in the same domain and you have that the sequence converges uniformly to the limit function f, then of course everything will be okay. Right? It's relatively easy to just show that, the function will be analytic, all the limits are what you expect. You can move limits inside and out of the integrals, everything is okay, right? Usually when you have uniformly convergence, everything is fine, right? You should work out each one of the properties just to make sure, but usually everything is okay because the error terms start being bounded uniformly, and you can just take them out and bound them uniformly with absolute values and so on, everything is okay. But oftentimes we want to talk about convergence of things that don't converge quite uniformly. And so what we want is, what is the right notion of convergence, right? What should we ask for, right? What should we ask for? So that one still implies that f is analytic. Okay. 2 is general enough. And 3 is easy to check. Right? This should be the goals. Okay, so I'll just, in the next 2 minutes, so if we're taking 2 extra minutes, I just want to show you the theorem. Okay, and then I'll prove at least part of it next on Friday. I mean, the proof of this is just, essentially the same type of tools that, I mean, the tools are a bit different, but the ideas are very much the same that you've seen already in other analysis courses, right? But one thing that's worth mentioning is sometimes f of n is defined in a set omega n, right, for different regions. Right. So this happens, quite often, in which you define f of n in a region that doesn't contain quite the entire region, right? And f, say, is defined in a region omega. Right? Maybe you have, but it's important, of course, in order for us to talk about convergence, it's important that for all z in omega, there exists some n0 such that for all n bigger than n0, right, z is inside all the omega n's, for z is inside all the omega n's, right? So you should think of, it's okay if omega n starts small and is growing, right, and it converges to some omega, as long as of course, for you to talk about limits, you need to be that for every z, at least there is some n such that for any n bigger than that, all the functions fn are defined and analytic there. Okay. And in fact, the example almost always, like the example of interest, examples of interest, you should think of the omega n's as being, omega 1 being inside omega 2, inside omega 3, and so on. Again. And omega is just the limit of this, so it's just a union for n1 until infinity of omega n. Right, so think maybe you have, like maybe, omega n is like the set of z's such that z is smaller than 1 minus 1 over n, right? So you stay a little bit away from the boundary of the disk by a 1 over n, but you converge to the disk, right? These are the kind of examples that one studies. And then the right notion of convergence, actually, in order for us to do what we need to do, will be that convergence happens uniformly in compact sets. Okay, so I'm going to write the theorem because it's a good theorem to have. So this is a theorem due to Weierstrass, and then I'll prove it, at least part of it, next Friday. Weierstrass, I don't think has an E. Okay, so if you have Fn analytic in omega n, okay, and Fn, right? So Fn as n goes to infinity, goes to function f in omega, right? So in particular, for any z, this needs to be defined. So omega n needs to contain z after a certain n, like uniformly in each compact subset of omega, then f is analytic in omega, and the derivatives, right, uniformly in each derivatives f prime uniformly in each compact set. Okay, so why uniformly in each compact subset is important? Okay, just before we finish, let me just say a word, which is why is it, so this is the theorem we're going to use. This turns out is sort of general enough, easy to check or relatively easy to check, and it gives us what we want. And why is it important to be uniformly in compact sets and not actually uniformly on it? First of all, uniformly over compact sets is much easier, right? Because continuous things in compact sets have a maximum. So, you can take the maximum of the deltas and you can do things like this, right? And the other thing is that, or the maximum, minimum, and so on. So the other thing is, the reason why sort of uniformly in each compact set is enough is that because of Cauchy integral formula, or say Morera's theorem, we can argue that a function is analytic by via of integral formulas. For example, if a function integral is 0 around any curve, closed curve, then it must be analytic. But all the curves can be contained always inside a compact set inside omega. So you can make all the reasoning about curves, integrals over curves, inside a compact set. And if things converge uniformly, then everything in the integral will be okay. And so you get everything you want just from this. And then proving uniform convergence on compact sets will be very easy. And so this is sort of the right trade-off between, generality and easiness to check. Okay, sorry for taking a few extra minutes, but I just want to, you might use this theorem in exercise class. I just wanted you to see it, and then Friday we'll prove it and take some exploiting some implications of it. Okay, sorry for taking a few extra minutes. I'm happy to stick around, however long, to answer any questions or anything. Just please ask if anything is not clear. And feel free to unmute you right on chat. Now it's easy for me to read the chat.